Good morning. In this video, we're gonna talk about practice problem number 23 from OpenStax College Physics, motion equations for constant acceleration in one dimension. So we have this problem. It says a light rail commuter train accelerates at a rate of 1.35 meter per second squared. How long does it take to reach its top speed of 80 kilometer per hour starting from rest? Essentially, so we're being asked here for how long is what how long is the time. Okay, now since this problem is under constant acceleration in one dimension, allow me to write first all the equations that I know. There are only three that I normally use. V final is equal to V initial plus AT. The other one that I normally use is delta x, or meaning the displacement s, is equal to VOT plus 1 half AT squared. And lastly, I'm using 2AS is equal to velocity final squared minus velocity initial squared. Now note that there are some variations to the notation, but this one is displacement. S here corresponds to displacement. Now for problem A, it's asking us to what? To find how long does it take to reach its top speed. So the train, if we try to visualize it, the train might be on this rail, in this track, and the train might start somewhere here. Let me draw a blue train. So the train, okay, the train might be here, quite a long train, and it's able to what? It's accelerating, and somewhere here at this point, maybe now it has what attain a speed of v equal to 80 kilometer per hour. Okay, and note that we're looking for the time how long. And in this case, the idea, I think you can relate to this, that this is starting from rest. Starting from rest means v is equal to 0, and we're looking for time, t equal to what? So in part A, it's as simple as using the first equation, right? Vf is equal to Vo plus AT, because this is the only equation that is what? That involves V final, V initial, and acceleration is also given. A is given here to be 1.35 meter per second squared. So a simple plug into the equation. Let me see. V final, that's 80. I think the problem here is one of the problem also will be that our V final is given in terms of kilometer per hour, and normally we want to convert this to standard SI unit, meaning it must be in terms of meter per second. To do that, we can convert the what? The kilometer to, we can just have here that 1 kilometer is 1,000 meters, okay? And convert the hour, 1 hour, hour must be in the top, 3,600 seconds, okay? So that same thing, let me calculate on that. 80 kilometer per hour, 80, okay, times 1,000 divided by 3,600. That gives us a 22.222. So 22.222 meter per second. So that's the one that we'll plug into the equation. Okay, this equation, Vf is equal to Vo plus At. So let's have that here, 22.222 meter per second. I'm dropping the units now. You may or you may include the units. If you are already confident, you may drop the unit. But if you are still not so sure about your steps, I suggest you include the unit. So 1.35 meter per second squared times t, time here is then the one that is unknown. Okay, so to solve for time, we simply divide both sides by 1.35, right? So divide that by 1.35. That gives us a 16.5 or 16.46 seconds. 16.46 seconds. So meaning it it will take this train 16.46 seconds to what? Starting from rest to get into its top speed, which is 80 kilometer per hour. That's the answer for part A. For part B, the same train ordinarily decelerates at a rate of 1.65 meters per second squared. Now, this train normally slows down, okay? Meaning, this train will slow down to the speed of, okay, let me show it in the drawing. Okay, here, this same train will slow down somehow. it will slow down. Slowing down meaning decelerating means slowing down until it stops. Okay, so how long does it take to make this train come to stop? Okay, from its stop speed. So meaning here v is equal to 0, meaning this train is moving fast and it's slowing down for we don't know how long. So this we're looking also for t there, and we are given that the deceleration a is equal to 1.65. And note that we need to take note that when we say deceleration, it means what? Negative. The acceleration there is negative because it means it's slowing down. A positive acceleration in this case, in this will mean this the speed is going up. But in this case, we know that it is slowing down. So the given 1.65, you need to take note that there must be a negative in there. Okay? So we use the same equation. Vf is equal to Vo plus At, but this time, okay, but this time we will be Vf is now the 0, meaning this is our new initial and this is our new final velocity, okay? Because this is now a different scenario. So V final is 0, and initially the train is moving at top speed, so 80 kilometer per hour, that's 22.222, so 22.222 in terms of meter per second, okay? So because we are using standard SI unit, and then here, take note that you need to put the negative 1.65, okay? That's for the acceleration, and then the t here is what is unknown to us, okay? Therefore, if we work this out, meaning transfer 22.222 both sides, I mean subtract 22.222 to both sides and then divide by negative 1.65, we will be getting a what? Let me see. 22.222 divided by 1.65. Okay, I hope you know how to do the math for that. It will be 13.47. 13.47 seconds. This simply means that this train needs 13.47 seconds from its stop speed to stop. Okay, meaning it needs that time for it to stop. As you can see, it's a lot smaller than this one because the deceleration rate is quite bigger than also the acceleration rate, which is 1.35 only. Now, in emergencies, the train can decelerate more rapidly, meaning, oh, the normal case, it will take it 13.47 seconds, but during emergency, that the train needs to stop, at faster time. Here, decelerate from rest from 80 kilometer per hour in only 8.30 seconds. Now, what is its emergency deceleration in meters per second squared? So, in part C, we're now looking for what is the deceleration. So let me note that here. The same equation that we'll be using, okay? We'll use the same equation, Vf is equal to Vo plus At. But during this case, now we know Vf it will stop. Okay, Vf is 0. Vo is still moving at stop speed, 22.222 plus A, and we're looking for T. And I mean, we're looking for A in this case. T here is given to us, which is 8.30 seconds. And if we solve A from this equation, I hope you already know how to do that for now. Meaning we transfer the 22.22. Okay, if we do the math for that, that will be equal to 130. You will get a negative 2.68. Negative 2.68 meters per second squared. And therefore, okay, if you do the math for this, okay, and therefore, the deceleration is the negative there simply means it's deceleration. Deceleration is 2.68 meter per second squared. Okay? So I hope you learned something from that. Thank you.